Okay. Good evening, everyone. Welcome to week 8 of linear algebra through geometry problem solving session. My name is Bhavya Rai. I am a PhD scholar at IIT Madras. Okay. And so this week we'll be looking at vector spaces, okay, and concepts like dimension, rank, basis, and so on. And it's a very a nice interpretation of vectors, geometry. Okay, a very fascinating type of concept. So, and we'll be solving some problems regarding the same. So, okay, it's 10%. Okay, so I'll just look at vector spaces. Okay, and vector spaces, we'll be looking at things like, of course, vector space in itself, the definition, okay, how it's related to vectors, and what is a subspace, okay, and what is a basis, what is the dimension, and this will be the major topics of interest in this session. Okay, now before we get on to the problems, I just want to briefly recap on the lectures what a vector space is. Okay, a vector space can be interpreted in two ways. Okay, so a vector space can be interpreted as a collection of vectors, but it does not mean that any collection of vectors is a vector space. It's a special collection of vectors. Okay, and but what is the other way and a more general definition to look at it? A vector space is a set of elements. You need not interpret them as vectors. Okay, set of elements that satisfy the following. Okay, and there are 10 axioms. Okay, there are 10 axioms that make vector space a vector space, and it is just a set of elements that satisfy the following. So upon doing vector addition, okay, there are two types of operations that you can do: vector addition and scalar multiplication. And on vector addition, it should be closed. Okay, so closure, rather, I'll say. And what does closure mean? Well, if you have two vectors v1 and v2, and if they belong to a vector space, then if and only if v1 plus v2 belongs to the vector space. Okay, and it should also be closed under scalar multiplication, so which is actually point number 6. So it's again closure with respect to scalar multiplication, which means if you have a vector v which belongs to a vector space v, if and only if you multiply by a scalar k, okay, this is a vector, k is a scalar, okay, then that belongs to the vector space. Okay, so in other words, if you expand or shrink that vector, it should belong to the same vector space. Okay, so these are two of the more important properties. Okay, and there are other properties which are like commutativity, which just means that v1 plus v2 equals v2 plus v1. They commute under addition. Then the next property is associativity, okay, which just means that I can add v1 and v2 separately first, and v2 plus v3 separately, okay, and it will still be fine. And additive identity existence of identity, which simply means that there should be a vector which we call a zero vector. There should be a unique vector which is called a zero vector, which when I multiply, which when I add with v, I should get the same thing. Okay, it does not, also it is commutative, so it does not matter whether you add it from the left or to the right. Okay, and finally, in terms of addition, you have the additive inverse. Okay, which is just a consequence of additive identity, which is that if I have V, for any V in V, there exists a V inverse such that V plus V inverse equals the additive identity, which is the zero vector, which is called the zero vector. And similarly, there are properties here too. Okay, similarly, there are properties here also. So that is associativity. Okay, but what does associativity even mean? Because here we have like a binary operation. So we just have k times v, right? So what do you mean I multiply one first, the other first? It means like in terms of a double scalar multiplication. So I multiply with k1, k2, v. It does not matter if I multiply k1, k2 separately or k2 and v separately. Okay, so this is some terms of some kind of associativity. And then we have identity in terms of multiplicative identity. Okay, so which simply means that there should be a vector, okay, which when I multiply with, I'll get the same thing. So this is called a unit vector, right? One vector. And then I have distributivity. And this is of two kinds. It could be distributivity over scalars or vectors. So this simply means that if I have a k and vectors u and v, which I'm adding, k distributes over u and v. So you may have seen this property in, say, fields or in integers, say, that anything distributes over the addition. And we have the other kind of distributivity, which is over vectors, which means that if I have two scalars k1, k2, and I have a vector v, then v distributes over k1. Okay. So these are the, it needs a bit of charging. So these are the 10 properties or 10 axioms that make up a vector space. Now, what are the most important properties? By important properties, I don't mean that the others need to fail. Okay, others can fail. Everything, all these properties need to be satisfied in order for the set to be a vector space. Okay, but which are the most important properties? Firstly, it's closure on addition and closure on scalar multiplication. Okay, associativity, commutativity, and so on usually are not a problem. Okay, and another thing is the additive identity, which is the presence of a null vector. Okay, now this is like the definition of a vector space. If you want to check whether something is a vector space, then it should satisfy all these properties. Okay, but if you try to imagine now, not in terms of just a set of elements, but a set of vectors now. Okay, a set of vectors. What forms a vector space? What do you mean by a vector space? So by the definition, it means that it can be a bunch of vectors. So as you can see, if you have a bunch of vectors, it may be okay. So let's do this. Okay. Now you have a bunch of vectors, and you want to see if they form a vector space or they lie in the vector space and so on. There are so many vectors. Now, what you firstly observe is, you know, they satisfy properties like commutativity, associativity trivially because they are vectors. Okay, so if you have any, you know that if you have any two vectors, then let's say a, b, and c, d, they are commutative. You know that the addition is commutative. This is usually not a problem. Okay, when you are talking in terms of vectors, but The important properties are something like closure. Something like closure. What does closure under addition means is that when you combine these two vectors to get a resultant vector, okay, this vector should also belong to that set of vectors. Yeah, Kishore.
Yeah, see, as per the definition, we are what we are saying is we are comparing these laws between two vectors. But
We are
whereas
comparing what?
we are comparing those 10 laws
Ha, ha.
with between the two vectors.
For all vectors, depending on
Uh,
the context, for all pairs or for all vectors. Yeah, that's
so
right.
so when we say the definition of
Uh,
vector space, it's more than two vectors, right? It would be more than two vectors.
no, it's not necessary. For example, see, this is a vector space.
Okay, then more than
Okay.
one vector.
No, that's also not necessary. For example, this is a vector space, trivial vector space. You only have the zero vector.
Okay, so
Uh,
based on the definition, to pertaining to my doubt,
uh,
so let us suppose vector space has one vector, two vector. That's okay.
uh.
About if more than two vectors, how we compare these laws to, is it something that should be
Yeah. Yeah,
compared to?
that's a good question. That's a good question. We'll see that.
Okay,
Okay. Basically, of course, given an arbitrary vector space with very strange, maybe they don't have any pattern associated with the entire space, then it will be difficult. I agree. But if they, all of the vectors in the vector space, if they have a certain property, we can test it. Okay. We'll see examples. We'll see lots of examples. Okay. Oh, okay. I think Satinder had raised his hand, but yes, I think he'll join back. Let's see. Okay. Um, yeah, where were we? Okay, great. So yeah, that is something that we'll see. Okay, Kishore. And now, now, then, what do you mean? What does closure? What does closure actually represent? Okay, closure. What does it represent? What does the closure property represent? It represents linear combination, right? If a set of vectors, if a set of vectors, okay, is respects the closure property, okay, which means if I add two vectors, okay, this is a set of vectors. If I add two of them, okay, I'm going to get a third vector in the same space, in the same V, okay. And it also, the if it is closed under multiplication, scalar multiplication, it means if I have this V, I multiply it by k times, okay. Hi Satinder, you had raised your hand that time, no?
No, I've not raised my hand, sir.
Oh, okay. No, okay. That time I think maybe it was by accident. Okay.
Actually, I was disconnected in between, actually,
Oh, okay.
due
Okay.
to some
Sure.
problem.
Oh, okay.
Thank
Sure.
you.
No, no problem. Okay. So what does closure mean really? So if I multiply, if I add, I get into the same space. Okay, in the same set. If I multiply by a value k, I get some. Let me. I'll get some k times v1. Okay, which belongs to the same set, right? Oops. Right. So what does it mean? It means this is just linear. This is just linear combination, right? You're adding two vectors. Means you're taking a linear combination. You're multiplying a vector by a scalar. Then this is just taking a linear combination, right? So closure that simply means closed under closure under addition and scalar multiplication simply means closed under linear combination. Okay. Okay, so now what? So what is a core thing that we see? That if I have a set of vectors, okay, if I have a set of vectors, what I'll simply do is I can form a vector space in the in the following sense. I'll take the two vectors. Okay, I'll take any pair of vectors which I start with. I'll add them. Okay, I'll add these two, and then I'll get a third vector, and maybe I'll multiply this multiply also by k. Then I'll get this vector. Okay, and I keep doing that. So I have this new vector. I'll multiply it by another k, let's say, and I'll put it in the same set. And maybe I'll add these two and then get another. So what I'm doing is I'll take any beginning with any set of vectors v1, v2, and so on till vk. Okay, v1, v2, and so on till vk. And then what I'll do is take all possible linear combinations over, let's say, reals. Okay, so that's what I will do. This almost forms a vector space because you know now that this set is closed. Okay, because no matter what linear combination you take, it will be inside. I mean, that vector will be inside this set. And this is also called the span. This set is also called the span of v1, v2, and so on. Now, but why is this almost a vector space? Which property does it violate here? I mean, which property may it may violate here? Is this property? Is this property? Zero vector should always be in the set in order to qualify as a vector space. Okay, so additionally, if it is possible to generate a zero vector using v1, v2 till vk, or one of v1, v2, vk is a zero vector, then this will definitely form a vector space, because all the other rules are, by vectors they are trivially satisfied. Associativity, commutativity, and so on under addition, multiplication, whatever. Closure is something you need to check for vectors. Okay, whether on adding, on doing linear combination, you'll get to the same set or not. And the other thing is whether zero vector will be in that set or not. As soon as you put the zero vector in that set, this becomes a vector space. Okay, and now we'll move on to the question, but just a small addition. Okay, what does it mean geometrically? What does it mean geometrically? If I take two vectors, suppose. If I take two vectors, suppose. Okay, if I take two vectors, what does it mean geometrically to take its linear combination? What happens if I take the set of all linear combination? Geometrically, what is the interpretation? Any idea? If I take k1 times v1 plus k2 times v2, this set of vectors, geometrically, how will it look like?
So we'll get another vector into the space.
We'll get another vector, let's say here, okay, but we won't just get one vector, no. We'll get multiple vectors because I can vary these k's.
Yeah, exactly. It goes on increases as we compare the laws.
Exactly, but what is the important thing, that even if this varies, they will all lie within the same plane. Is it not? They cannot escape the plane.
What do you mean by varies?
What I mean is, if you take different values of k1 and k2.
Yeah.
Okay, if it will always lie on the same plane that v1 and v2 lies in. It will never escape that. You get it? So geometrically, what does a vector space represent? vector, let's say a span of vectors, okay, represents, for example, the span of v1 comma v2 is this red plane. It's all possible linear combinations of v1 and v2. Now, additionally, what you want for it for span, when is the span of v1 v2 a vector space? It is a vector space. Okay, span of v1 v2 is a vector space if the zero vector belongs to if the zero vector belongs to the span. If the zero vector also belongs to the span. Right? I hope you are convinced of this answer, because this represents the additive identity. Now,
Is this vector space and span of vector isn't the same, or they are different?
Good question. Vector space and span, will every span always be a vector space? Not necessarily, because zero vector should be in the span for it to be vector space. You get it?
So may know the difference. Maybe it's very thin line difference.
Sure. I'll tell you the difference. Okay. I'll tell you the difference. For example, take the set 1, 0 and 0, 1. No, this is not a vector. This forms a vector space. Let's see. Okay, this is trivially not a. Oh, okay, yeah, okay, I have it. I think 0, 1, 1. One maybe. No, this also will not form a. So for example, okay, I'll take the trivial one. Yeah, if I come up with a better argument, I'll let you know later. For example, this. Okay. Yeah. Okay. Okay. So okay. No, yeah. Sorry, I think I was a bit wrong. A span will form a vector space because in a linear combination, if you take, let's say, v1 and v2, I can always set to alpha equals 0, beta equals 0. So the span will always be.
So can we say span is the tiny version of the vector space?
No. You can't exactly say that. Span is a vector space. Okay, but it is a vector space. The span of a set of vectors forms a vector space. Okay, so I made a small mistake here.
better understand. Is it possible quickly? Can we show it on graphically? Is it this?
Yeah, that was what I was going to do. That was the point of getting into this. Okay, I'll show you graphically. Okay, So, okay, so you have this. So it means the span is also a vector space. But okay, so I want to restate what I said. Okay, any set of vectors, any arbitrary set of vectors may not be a vector space. Okay, for example, say the set 1 1 0 0 1 0. I'm not taking the span of this. I'm not taking the span. Okay, this I'm claiming to be my set S. Is this a vector space? The zero vector does not belong. Is not in S. So it is not a vector space. Okay. Now, but of course, I can always find a plane through which both of them will pass, right? So why? So what is the idea? Okay. So what is the idea graphically? Even if I have a set of vectors, graphically, even if I have a set of vectors, it needs to have a zero vector. So what does it mean when the set of vectors needs to have a zero vector? It means that it must pass through the origin, because this is the zero vector, right? So if I have a set of vectors, let's say represented by a plane, it needs to pass through the origin. This is an important thing. But if I take a span of v1 v2, it will definitely pass through the origin, because I can always do 0 v1 plus 0 v2. This will always give me the zero vector. Okay, is that clear?
So is that when we say it has to be passed through origin, each and every vector in the space in the vector space, we mean?
Meaning each and every vector.
Oh.
No, sorry, not each and every vector. There should be a linear combination of v1 and v2 that is equal to 0, which is equal to 0. In other words, if I have a set of vectors v1, v2, and so on, v3, and so on, which are on this plane. Okay, v1, v2, v3, and so on, which are on this plane. They all need to. You should have a linear combination of v1, v2, and so on that actually passes through the origin. Is that clear?
Yeah, at least one vector should be such like that. It should pass through.
Yeah, it should exactly be the origin.
Okay.
Okay. So it means that the entire plane should pass through the origin. Okay. I hope that's clear. Okay. Okay. So that was just a quick recap. So now let's try to solve some problems. Okay. Okay. So here's the question. Let V be the vector space of all continuous real valued functions on 0, 1, and define W to be this set. Okay, all the functions in that vector space V. So V is already a vector space. V is already a vector space. Okay, and you are given a W. And what is V? V is F such that F is a real valued function which takes a real number and maps to somewhere between 0 and 1. Okay, so there could be infinite F's. But the idea here is that f can be interpreted as a vector, but not necessarily, because vector space, the definition is general. Okay, if all those properties are satisfied, then it forms a vector space. Okay, so f may not naturally be a vector. Okay, that's what I mean. Now, this is V, and then you have W. Okay, now W is f in V such that f of 0 equals 0. Question says prove that W is a subspace of V. Is W a subspace of V? Now, what is a subspace? A subspace is W will be a subspace of V if W, the set W is contained in the set V, and W is a vector space. Okay, it is a subset and it is a vector space itself. Then W is called a vector space. Is that clear? Now,
when you say W belongs to vector space, that itself means that it's a vector space, right?
No, we are not saying W belongs to vector space. I'm defining a subspace, right?
No, for the first line of which you.
No. This does not imply that V is a vector space. For example, a simple example is a simple example is x such that x belongs to real numbers. This forms a vector space. Okay, I'll write it separately. Question is S a vector space or not? Okay, is S a vector space? Well, what will S look like? S looks something like 1, 1, 1.5, 1.5, 7, 7, and so on. And this is what it looks like. Now, is it a vector space? Now, I'll just test closure and additive identity. Okay, so is it closed? Let's see. Is it closed? Let's see. If I take any two vectors in S, if I take any two vectors in S, which is always of the form A, B, B, C, C, and so on, if I add them up, I'll get A plus B, which is of the form X, X, right? So it's closed under addition. Now let's see if it is closed under scalar multiplication. If I take AA and multiply it with the scalar K, it is nothing but Ka, K, but which is of the form X, comma X. Now finally I'll check addition, not addition, I'll check whether null vector is there. So null vector is what? 0, 0. Is it in S? Yes, it is in S because it is of the form X, comma X. So are you convinced that this is a vector space?
Also the inverse and as well as multiplicative identity.
Those are because it's already in a vector form. Those are satisfied. You don't need to worry about that. If it was something like functions, then I would agree. But vector addition is always commutative. You get it, right? Vector addition is always associative. So anyway, it's already given to me as vectors. I don't need to test it technically.
So the thumb rule is what we should check initially. I mean, at least is the closure as well as the null vector.
Null vector, exactly. If it's already a set of vectors. Okay, in this form. But like you see here, right? Now we have a set of functions. Now we cannot say that, oh, obviously, when the order does not matter and things like that. We cannot say easily. That we need to test. Of course, here also you are not losing anything by testing. Okay, it makes sense to do a sanity check. But if I tell you something like, oh, now check if let's say you want to check, say, commutativity, then you'll do a plus b equals a plus b, and check b plus a equals b plus a, which is equal to a plus b, and these two are equal, and then you'll say that yes, commutativity is also expected. But you see that this does not tell us anything new, right? Because they are already in vector form, and you know that vector addition is already commutative. But yeah, here if you cannot say that directly because they are some functions, and if you don't know easily whether f1 plus f2 equals f2 plus f1, so on. You need to do a bit of analysis to understand. Okay, so yeah, so where were we? Okay, so I'll remove this. Okay, now you're convinced, right, that this is a vector space. S is a vector space. Therefore, S is a vector space. Okay, now I'll take some S prime, which is 1, 1. Okay, now I ask you the question, is S prime a subspace of V, of S? Okay, is S prime a subspace of S? Now I told you if S prime is supposed to be a subspace, then it needs to be a subset of S. Correct. Second property is S prime is a vector space. This we need to test. Now let us test that. If S prime is a subspace, is it closed under addition? Yeah, you just have one element. No. Oh no, it's not necessarily closed under addition. Because if I do 1, 1, what will I get? I'll get 2, 2, which does not belong to S prime. Because S prime only contains 1, 1. It's not closed under addition. Is it closed under multiplication? Scalar multiplication? 1, 1, k times 1, 1, which is, let's say, 2 times 1, 1 equals 2, 2, which does not belong to S prime. This is also violated. Any one violation is enough, and 0 vector, more specifically, does not belong to S prime. So even this is not satisfied. Therefore, S prime is not a vector space, and S prime is not a subspace. So you see, right, that being a subset does not mean it's a subspace, because S prime was a subset. So does that answer your question? Okay, great. So now we are asking, is W a subspace? Oops, is W a subspace of V? We are asking that. Now we'll check that. Okay, to prove that W is a subspace of V. Now W is this. Okay, so let's we need to check all the properties like closure under addition. Is it closed under addition? Firstly, what does it mean to add functions? Right. So if I add two functions, I need to come up with some kind of definition what I mean by addition. So let's say adding two functions simply means, yeah.
Excuse me, sir. What you're writing, I think it is not visible on my screen. I think so.
Oh no, is it okay? Kishore, are you able to see it?
Yeah, I can see.
So should I disconnect and connect it back?
Yeah. Can you do that? We'll wait.
Yeah.
Okay.
Maybe it's due to internet lagging.
Yeah, could be. I hope it's not from my side. Yeah, Satinder, are you able to see it now?
Yes, sir. Thank you, sir.
Okay, great. Okay. So, as I was saying, what does it mean to add two functions? Okay, so the most natural way to add two functions would be that I, if I say f1 of f2 and a function always takes an argument, then I'll take x, I'll take the evaluation over x and add it to the evaluation of the second function over x. So this is a very natural thought, right? So, this is what I mean by adding functions. So is it closed under addition? Let's see that. Okay. So if it needs to be closed under addition, oh, okay. Sorry. By the way, before we test that it's a vector space, we should test whether it's a subset. No. So the first test is whether W is a subset of V. You see that V is a set of functions that takes real numbers and maps to 0 or 1. I mean, not 0 or 1, something between 0 and 1. Okay, real numbers between 0 and 1. Okay, so let me write it diagrammatically. So what is V? It's a set of functions of this form. So this is takes a real number and maps to somewhere between 0 and 1. Let's say it took 10.2 and mapped it to say 0.01, and it keeps doing this process. Okay, and the set of all such functions, take the set of all such functions, that is V. V is the set of these kind of functions. What is W? Now let's see what is W. W is the set of functions which takes a real number. Okay, W is just a function in V already. Okay, so we didn't even have to check it, because already we are saying that W is the set of functions which are in V. But additionally, there is this property. Okay, so this already tells us that W is a subset of V. Additionally, so if it's a function in V, then it takes a real number that maps somewhere between 0 and 1. Okay, since it's a set of functions in V, but additionally f of 0 equals 0. So I have things out here, right, in real numbers, the entire real numbers, but then I have 0 out here. This 0 is always mapped to a 0, and the rest could be mapped arbitrarily. So take all those functions where this restriction is there. 0 is always mapped to 0. Okay. That is what W looks like. Now yeah.
See, when we say f belongs to V, that it means that it already we said that if 0 also belongs to, I mean, like 0 contains in F.
0 contains in F. No, F is a function now. F
is a function, right?
Yeah.
So F belongs to V, we said. F belongs to V.
Oh, but see, F belongs to V. Additionally, it has this condition. But it's not all the... no, it's not everything in V. It's only those functions in V which take 0 as input and output 0 as output. Okay, so if you do f of 1, then it may give you something else. That's fine. But f of 0 will always give you 0. But notice that in the case of V, this restriction was not there. If I took a 0, then from real numbers, then I could map to say 1 or 0.2.
So by the statement, right? If we take the set of W, it only contains one element, that is 0.
No.
Can we say that?
No. W is a set of functions. So I'll give you an example. So here is one function. F1 is 0. Okay. When f1 of x is 0 when x equals 0, and f1 of x is uh, 0.5 otherwise. f2 of x is 0 when x equals 0, and it is 0.3 otherwise. Or let's say f3 of x equals 0 when x is 0, and it is let's be more creative. F3 of x is nothing but if it is x is a real number, it is 1 by 10 to the power the length of x. Okay, number of digits in x. Times x. So in the case of f3 of 3 equals 0.3. f3 of 0.045 will be equal to f3 of 4509 will be 0.4509. Similarly, f3 of 0 will be equal to 0.0. I mean, you get the idea. But notice that all of f1, f2, f3, they are contained in W. Is it not? W is a set of functions. That is the main thing. But it is the set of those functions. Okay. Firstly, those functions which are in V, which means it takes a real number, maps somewhere between 0 and 1. Additionally, those functions have this peculiar property that when you take 0 as input, it will always output 0. Okay. Now we need to test closure under addition. Okay, closure under addition. Let's see. So that's what I was saying. Now you need to say what does it mean to add two functions. So the most natural idea of adding two functions, okay, f1 and f2, would be defined in the certain sense that f1, f2, okay, the addition of f1, f2 is of the following sense that if it takes x as input, then it does f1 of x, then f2 of x. So this is the most natural way which you can think of addition of functions, right? Now, is this closed? Is this closed? Let's see. So is this in W? That is what we are asking. If is f1 plus f2 over x in W, or just f1 plus x2, let's not parameterize it yet, in W, if why is it in f1, f2 is in W? Okay, so this is the closure property, statement of the closure property. Yeah, Kishore, can you tell?
Yeah, I was saying it is in closure.
Okay, because okay, there is. Okay, now I'm thinking it's not.
So no. I think. See, let us suppose. I think it's not. So let us suppose for f1 of x, it is 0.9,
Exactly.
and then f2 of x, it's 0.9 again.
Exactly.
It is beyond the 0. Beyond 1.
Exactly. That's right. That's right.
So it's not. It's not.
Okay. So let's slightly modify the question. Okay. Let's say addition of function is defined as to just in order to normalize it, f1x plus f2x. I think now it's fine, no?
Yeah, that's also fine. Or else we can add a restriction or condition on the function definition itself, stating less than.
No, that we cannot do because then you'll need to change the definition on. Oh, you mean change the definition of w?
No. If we wanted to make a slight change, right?
Huh.
Probably we can do that slight change in the definition of the function. Is it possible?
Definition of the function. Oh, you mean this part?
In the question, yeah, in the question, yeah, right? No, not in that. In W.
In W, this.
Yeah, in W, what we can do is x should be, less than 0.5. Less than or equal to 0.5. In that case, right, 0.5 plus 0.5, it's at a max we'll get.
Oh, okay. So you mean change the domain of the function? But will that be a subset? It won't be a subset. That's what I think. It can. Oh, yeah. It can be a subset.
0.5 is a subset, and 1 also subset. Or
Yeah, it will be a subset where you are shrinking the. Yeah. Okay. Yeah. That is another. Yeah. Good. Okay. Works. Okay. Sure. So yeah, if you consider divided by 2 or like what you mentioned, 0.5 maximum input, okay, then it is closed. Let's see closure under multiplication, scalar multiplication. This too will be a problem because this too will be a problem because if f of something, let's say f of x is equal to 1, then k times f of x is defined as, say, k times f of x is just k, where k is a real number, right? So again, this creates a problem. What could be? How do we force it to be a vector space? Then? How do we force it to be closed? Well, can we close it? Under scalar multiplication.
Same. The k value should be within 0.1 itself. 0 to 1. 0 to 1.
Well, see, the thing is, you can do that, but it's not a neat way because you can do that. You can take the coefficients to be, but it does not form a neat vector space. That is true. Yeah,
exactly. But as it is a function, if we add that condition to the problem statement, probably that becomes the vector space. But whereas,
so that if you do one small thing, then it will work. I think.
But whereas for the existing problem statement, the answer is no. We can say for both the questions.
Yeah. I think there is right. I think there is no other way that doing k belongs to 0, right? Instead of reals. Yeah, that's it. Right. Anyway, this was a very bad first question to start with. this was a very bad first question to start with because W is not a subspace. Okay. Yeah. So, but yeah, I think we can learn from the the bad design. So finally, the zero vector, okay, I mean, in this case, you need to check for the other cases also. Okay, for example, commutativity, associativity, and so on. And you need to check for this additive identity also, which does it exist that if you should be having a function. So this vector should be in your space in W. So it should be that G that when you add it, you get the same function. Okay, and then you get F basically, and then G will be your zero vector. So can that exist? Well, if you have f of x plus g of x equals f, then it must be that this is always 0. Yeah, then this exists because g is a function that takes any real number and always maps to 0, no matter what. So at least null vector exists, but the other properties are sort of violated, so this is not a vector space. So I don't think that this question is worth pursuing anymore, because the second part of the question also suffers from the same problem. Okay, so let's just move on. That's what I want to say. So let's look at the next part. Okay. Okay. So okay, now let's look at this part. Okay, this part is more interesting. So what you have are 4 vectors. Okay, what you have are 4 vectors v1, v2, v3, v4. You have to check whether these vectors are linearly independent. Okay, and now and if they are not independent, find one non-trivial linear combination that equals the 0 vector. Okay, first let's check if they are linear independent. We'll come to their interpretation soon. Okay, so how do you check whether they are linearly independent? What you'll do is you'll use the Gaussian elimination, right? Or you'll use the Gauss-Jordan elimination. For the sake of this question, let's use Gauss-Jordan elimination, okay? Because it will be helpful later. So how do we do Gauss-Jordan elimination? Well, what you'll interpret the question as a solution, a system of linear equations that you need to solve. Ax equals 0, and in this case, what is A? It is 1 1 0 0 0 1 1 0 0 0 1 1 and 1 0 0 1, and you'll take this modified matrix, okay, and augmented, which is called the augmented matrix, and here let's say x is equal to x1 x2 x3 x4. Okay, now what you are saying is okay, so let's proceed with the Gauss-Jordan elimination. Okay, so what you want to do is get to reduced row echelon form, which by using row operations. Okay, so what is the first operation? Let's try to remove this one. So I'll do R2. In R2, I'll do R2 minus R1. 1 0 0 1 0, and R2 minus R1 is 0. this is 1, this is 0, this is minus 1, right? Now I have 0, 1, 1, 0, 0, 0, 1. Now I want to eliminate this guy, so it will be R3. In R3 I do R3 minus R2. Okay, so what do I have? 1, 0, 0, 1, 0, 0, 1, 0, minus 1, 0, 0, 1, 1, 0, 0. Okay, now I see that I have two duplicate rows. So, but we'll continue the Gauss Jordan. I need to remove this guy, right? Because I want to get these pivot elements. So I just want one per row and one per column. Okay, so I'll continue. I'll do R4 minus in R4 I do R4 minus R3. Okay, so what do I get? I get 1, 0, 0, 1, 0, 1, 0 minus 1, 0, 0, 1, 1, and I get all zeros. And I hope you remember the pivot elements, counting the pivot elements. There are 3 pivot elements, but the dimension of the matrix is n. So what does this mean? This means the rank is 3. Right? And rank is less than n. Which is less than n? Which is less than n where n is 4. Which implies that the set of vectors are not linearly independent. Okay, the set of vectors are not linearly independent. Now, there are several things to learn here. Okay, so firstly, if the set of vectors are not linearly independent, then what is the linear dependence here? What does linear dependence means? From the 4 vectors that I started out with, one of the vectors can be created by other 3 vectors. That is the definition of linear dependence. And what is that one vector that can be created? Right. That is the first question that we have. Now, the second part is where the second learning happens, where we realize the definition of basis and so on. But first, let's do that. Okay. If these are not linearly independent, then what is the linear dependence between them? So now we'll see what is happening behind the scenes. Okay, what is happening behind the scenes? What we started out was with this ax equals 0. Okay, and the fact that what does this mean? And what is A? A1 is just V1, V2, V3, V4 times X1, X2, X3, X4. Which simply means that it is that combination of V2 scalars, linear combination using X3, V3, X4, V4 equals 0. Right. Now, here is the main idea here. Okay. So I do this entire process by using Gauss-Jordan elimination, and it so happens that I'm not getting I'm using row operations and so on, and I'm getting x1 equals, let's say 1, x2 equals 0, x3 equals something. It means that I'll get one of the vectors is dependent on the other. Okay, we'll understand what that means. Okay, so I have this look right now so far. So here I have, this is the on doing the row operations and so on. Now what does this imply? This implies that x1 plus 0x2 plus 0x3 plus x4 equals 0. Does that not? Okay, so that's what the first row means, right? Because we are multiplying it with the column matrix x1, x2, x3, x4. So the first row represents that x1 plus x4 equals 0. The second row represents x2 plus minus x4 equals 0. Third row represents x3 plus x4 equals 0. This is what it represents. Now, can we continue this process? Can we solve this? Okay, so okay, so using this, can we further simplify this? Okay, so we'll use something called parameterization, which means I'll just set x1 equals t. Let's see whether we can fix the rest. Okay, if x1 equals t, using equation 1, let's call this 1, 2 and 3. If x1 equals t, using equation 1, we have suppose x1 equals t. Okay, then using 1 we have what? x4 equals minus x, which is minus t. Now let's substitute x2, x4 here. So what happens if I substitute x4 there? Which implies that using 2, substituting into 2, x2 equals plus x4, which is again minus t. And now let's substitute x4, and again substituting x4 equals minus t in 3. What do we get? We get x3 equals minus of x4, which is t. Okay, so what does that mean? It means that as long as I set x1, x2, x3, x4 to be t, x2 is minus t, x3 is t, x4 to be minus t respectively, it will satisfy the set of equations, which means this set of equations is satisfied. Which means this set of equations is satisfied. Right. So it means that I can as well replace it with, okay, I can say that the solution is that I'll replace tv1 plus minus tv2 plus tv3 minus tv4 equals 0 for any t. This equation is satisfied. For example, if I set t equals 1, then what will happen? I'll have v1 minus v2 plus v3 minus v4 equals 0. What does it mean? If let's say I shift v4 there, I can do it to others also, but let's say I shift v4 there. v4 is equal to v1 minus v2 plus v3. Which says what? This is the linear dependence. I can create the vector v4 using v1, v2, v3. Equivalently, I can also say, which is same as okay, it's lost charge. Okay. Sorry. Yeah. Equivalently, I can say, for example, I can bring v2 to the right and say that v2 is equal to v1 plus v3 minus v4. So this also shows a linear dependence. Does not matter. It just says that taking linear combination of 3 vectors creates a 4 vector, which is a clear linear dependence. Yeah, Kishore.
See, by the explanation and doing with Gauss-Jordan, we proved that they are independent, linearly not dependent. But using like replacing with x value with the t, x is equal to 1, we deduced to some equation and then we proved it to they are linearly dependent.
So here, yeah, no, that's what. No, we prove that it is not linearly independent, which means it's linearly
Right.
dependent. Yeah,
Set of vectors are not linearly independent.
because if they were linearly
not
independent,
linearly independent. Okay.
yeah, not
Fine.
because if
Yes,
they were
sir.
linearly independent, their rank would be 4. Rank would equal to n. So
Right.
you would get this
Equal to
1,
n.
1, 1, 1 in the diagonal, all ones in the diagonal.
Yeah.
But you have a 0 row here, which means on doing Gauss-Jordan elimination.
No, literally, if you take set of vectors not linearly independent, then it means that they are linearly dependent.
That's right.
So when we get the pivot number as 4, that means what is the statement we'll get? Set of vectors
are linearly independent. If it's 4.
Linearly independent. Okay,
if it is 4.
Yeah. Right.
But I'm saying, okay. But additionally, I also mean that, this test tells you that there are vectors which are linearly dependent here. Right. This test tells you, in this case, that when rank is less than n, it tells you that there are vectors which are linearly dependent. Right.
So can you directly write set of vectors are linearly dependent here itself?
Yeah, you can say that. So yeah, this is a bit confusing. Yeah, I agree. So instead of saying not linearly independent, vectors are linearly dependent. Okay, this tells you this is a litmus test. No, but what I'm additionally saying is that this test is not just a litmus test. It will tell you what are the vectors which are linearly dependent also. Because this is nothing but solving a system of equations, right? What equation does it solve? It solves this equation, right? It is simply ax equals 0, because on the right we are putting all zeros, on the left we are putting the coefficient matrix. So it's just asking what is the set of x1, x2, x3, x4 that will lead it to 0. And what did we get? We get that any set for any t you take such that you take t times v1 minus t times v2 plus t times v3 minus t times v4. For example, here we took t as 1. We could take it as anything else. 2, 3, 4, whatever. It does not matter. Just for in terms of simplification, I took t equals 1. We got that v4 is equal to v1 minus v2 plus v3. Or equivalently, we can also say that v1 equals v2 plus v3 minus equivalently, you can say something like v2 equals v1 minus v3 plus v4. v1 plus v3 minus v4. We could have said this also, the same. But this also represents a kind of linear dependence. Right. Now, I want to ask you, so this represents linear dependence. When will it not represent linear dependence? When is it linearly independent? Okay, when is it linearly independent? As I told you, it is linearly independent. Okay, if it was linearly independent, then it would have something like 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. If it was linearly, by Gauss-Jordan, we know that if it was linearly independent, then this would happen. Right. But what would it mean? It means x1 is 0, x2 is 0, x3 is 0, x4 is 0. No? Right. Now, what does this mean? x1 is 0, x2 is 0, x3 is 0, x4 is 0. This equation is 0, is equal to 0 only if I take x1, x2, x3, x4 as 0. That is when linear independence happens. So So yeah, just one moment. I'll just finish writing this. So x1 v1 plus x2 v2 plus x3 v3 plus x4 v4 is equal to 0 if and only if, okay, if and only if x1, oh sorry, um, wait, sorry, the set v1 v2 v3 v4 are linearly independent if and only if this guy x1 v1 plus x2 is 0 when only when x1 x2 x3 x4 are all zeros. Okay, so this is a very important concept that you should keep in mind. Yeah, Kishore.
Excuse me, sir.
Yeah, sir.
So just I was thinking like this, if it is 3 cross 3, like suppose if you are taking 3 vectors,
Yeah.
so that forms a parallelogram. Parallel pipe.
That's right.
So if the volume of the parallel pipe is not equal to 0, it means it is linearly independent.
It means it's linearly independent, correct?
Okay.
Yeah.
So just I was concerned if I'm taking 4 vectors.
Yeah.
So actually they're what I'm finding. I can't say that it is volume, because if it is 2 dimension, I can say it is area.
That's right.
If it is 3 dimension, I'm saying volume.
That's right.
So if it is 4 dimension, it means that is also something it gives.
That's right. That's right.
So what it is giving means if 4 dimension is there.
That will not have a neat language in our sense. We'll call it volume only, but we'll call it a volume of a hyperdimensional parallelepiped. We cannot visualize it, Satinder. We cannot visualize it. We can come up with formulas for it.
No, I'm not saying to visualize. I'm saying two dimension is area, 3 dimension is volume. So 4th dimension is something it may be forming. So what is contained in that? So what name we are going to say that?
We can still call it volume. We can still call it volume only.
I don't think it will, because volume will be in 3 dimension. We can't. I think volume that part means
I agree.
For linearly dependent, what I'm thinking if 4 vectors we are taking and all the 4 vectors lies in the 3-dimensional plane, not in the 4th.
Then it will be a volume. Then it will be a parallelepiped.
That will be linearly dependent. Linearly dependent.
That's right.
And if I am taking 3, maybe means in lower dimension, it will be not in the same dimension. If it lies in the lower dimension, maybe 1 or 2. So it is linearly dependent. I think that will be there.
See, if 3 of them are linearly, if 4 vectors form a parallelepiped, it means at least one of them is linearly.
No. 4 are forming parallelepiped means it is linearly dependent.
That's right. And I agree that you want to think of only, you want to assign volume only to 3 dimensions, right? I mean, you want to assign the term only to 3 dimensions.
4 dimension, I think volume will be term will be not there. So what name we are going to give, or what does it?
Okay. So what you mean to say is you want the exact term.
I want to know that what it represents actually. 4 cross 4 determinant I'm finding.
Yeah.
So geometrically what it is giving. This time understanding it is giving determinant I'm finding. So it means that all the 4 vectors will be in the 4-dimensional space, not in the lower dimension. If that all will be in 4 dimensions, so geometrically what it gives, that I'm not getting that part.
So, see, I don't know if there is a particular term for it. Okay, I don't know whether there is a particular term for it.
Okay.
I would personally, I would say it represents some kind of volume only, but volume in higher dimensions.
What I'm thinking, if we can if we can look at this from like Earth atmosphere, whatever the things we are seeing, that is in the three-dimensional space. So
Right.
that we can different things we can assign as a vectors things.
Right, right.
So I can represent because I can visualize.
Yeah.
Now the Earth is contained in the universe.
Huh.
And if I'm able to some outer space, if I'm able to see the Earth as well as that space also from
Yeah.
somewhere,
Yeah.
so I think that view may gives the four-dimensional part. I think so, maybe like that.
You mean you can actually visualize that?
Actually,
No,
what core concept is there means the outside of the this universe. If I'm going means outside of the Milky Way, if I'm standing and I'm able to visualize the Milky Way in each of the object, and inside that may be the four-dimensional concept.
I don't think so. I see. The thing is, but now we are entering into, I don't know, physics and stuff. But
Okay.
the Milky Way and the universe all are.
No. Actually, I'm just thinking of this part only. Ki two dimension is giving area geometrically very well. We have understood. Three-dimensional part also very well we have understood. Ki okay, it is going to form a parallel pipe and how
Right.
the volume will be created.
Right.
But four-dimensional space, I think still it is the area of studies, means the research part, is something what it is going to give, or maybe someone has worked. I don't know actually. I've not gone through.
See, we cannot. Oh, okay. I think the bad internet has. Yes, Kishore.
For this question, right? So recently, have just come across one of the one article which popped on my mobile.
Okay.
See, one, of course, it's there always. One dimension, two and three. So these are the real-time applications we do have in place, and then we do have research journals in place. But for the fourth dimension, right? I think it's still under research. I'm not quite sure it is the fourth or fifth dimension, but we haven't have any such applications yet, which we apply them as a real time with more than third dimension. So it's under research still, I guess so.
Yeah, the thing is, the problem is we cannot visualize four dimensions, but we can still do mathematics with it. And I mean, we cannot visualize, say, like what is
the value comes when we visualize. Even though calculations we do, when we visualize it, it's based on the calculation, then the value comes to that calculation. So if we don't visualize, right, probably we are unsure that whether the calculation is right or wrong. We can't verify that.
No. I mean, that is the beauty of proofs in mathematics. You don't need to experimentally verify to say that it's true. If you have a mathematically sound proof to a theorem about four dimensions, and it just follows one after the other, you don't need to experimentally verify it. That is the thing about. See, for example, if I have some theorem, let's say Pythagorean theorem, it has a proof to it. Okay, it has a proof to it. Now, I mean, you can, given any arbitrary square, you can break it up into smaller parts and so on, but you can get a proof to the Pythagorean theorem. And the beauty in it is that once you have the proof, you don't need to experimentally verify it to actually see that it is true.
But we have that facility as well, the corresponding representation graphically or any other way for the respective proof, right? Till now.
Can you say it again?
2D, no. See, when we take an example of Pythagoras theorem, so of course it has been earlier due to based on the calculations, someone has given some proof. That's true. But corresponding to that, we also have some graphical or other geometrical proofs as well, right? Verifications.
Right.
At this time.
Yeah.
So going forward also, if we compare that to the four dimension, what do you say, verifications, of course there might be some calculations, but the research is still underway based on the article what I have read.
Yeah. I see if you are talking about, say, some kind of concepts in physics which depends on the experimentally verified laws of the universe and stuff. I agree that the research in the fourth dimension
See, what I mean to say is,
is
of
open.
course, we have some calculations in place in the mathematics, but to just verify that calculations are right or wrong, we have to have some verification. So that verification is under research. What I was saying.
So no, so yeah. I agree. So like if you're talking about, let's say, the fourth dimension in the universe, okay,
Right.
which is popularly said that it's the time. Time is the fourth dimension. That's what they say. I agree that if you are talking solely about time, which is a physics construct, it's not a concept in mathematics per se.
Right.
Mathematics is independent of
So
that.
that's where I was saying
Then,
the application.
then
So
yeah, then I
application
agree.
we haven't find it. So probably that's
Then I
under research.
Yeah, then I agree. Exactly. But if you are talking about a general fourth dimension, independent of like, if we are not just talking about our universe, just any fourth dimension, then I'm
Yeah.
just saying that we already can visualize it in a mathematical sense. Okay, but we
Okay.
cannot visualize it in a practical sense. Of course, that is true, and it will be generalizable to physics, but the opposite will not be true. That is, like, if you want to find something particular about the laws of the universe, then I agree, you need to experimentally verify it.
So taking your statement, like, see, irrespective of other laws. So if we take mathematically, we have proofs, and then we have proven that for the higher dimensions as well, right?
Right.
So are there any such applications we apply those calculations in real time right now, mathematically?
Of course. See, for example, oh, you use it all the time. I mean, see, myself, I work in theory, so I can give you theoretical
Okay.
applications of that in say, suppose Boolean functions. Okay, so you have Boolean functions. Okay, Boolean functions take um, uh, n bit number and then output a bit, 0 or 1. Okay, so how does the function behave? Well, you can make a truth table, right? Okay, you can make a truth table out of it and then see that, oh, okay, so suppose it's the XOR function, then it will only if there are even odd number of ones, then I can study it like this. Okay, some odd XOR will have something like this, truth table like this. But additionally, what I can do is I can imagine each of the placeholders to be a dimension, and then I can make a containment diagram out of it, which is something like 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and then the intersection of these two, that will be like, 1, 0, 0, 1, 1, and here the intersection of these two, which will be 1, 1, 0, 0, and then the intersection of these two, which will be 1, 0, 1, and then the intersection of all three is 1, 1, 1. Notice that it forms a cube. Notice that it forms a cube. It looks like a cube.
This
No,
truth table for 4 dimensions.
this is truth table for 3 dimensions.
Yeah. So can we have a truth table for 4 dimensions?
Of course, you can. You can.
Yeah.
So that's what is called the hypercube. So if you come up with 4-dimensional truth table, it will look like this: 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, and then you do this and 0, 0, 1, 1. Okay, and 0 1 1 0, and if you do these two, you get 1 1 0 0, and you do this, okay, and keep doing this. It'll form a nice structure which is called the 4-dimensional hypercube, Boolean hypercube. Okay.
Excuse me, sir. I was
Oh
battery
yeah,
was
yeah.
discharged.
I thought it was because of this. We were doing an offshoot of your your questions only. So we were
Okay.
Kishore was also adding.
Can I see from the beginning a little bit backward?
Yeah. No. So I was just explaining to Kishore that even though we cannot visualize the 4 dimensions, there are we can come up with mathematics for 4 dimensions, and we can apply them. That's what I was telling Kishore.
Okay.
So that's what I was saying. I was talking about, like, for example, in my field, we have these. We need to work with these Boolean functions, and Boolean functions are can be represented by truth tables like this, and they can be represented by a cube like this. And if I can highlight those, for example, like I was telling Kishore, that for example, look at parity. Okay, the odd number of ones. These are exactly the odd number of ones. Okay, Kishore, which I've so that parity as an XOR function. And similarly, if I take a higher dimension, then this is what it will look like. This is called a Boolean hypercube on 4 dimensions. This is also popularly called a tesseract. Okay.
So is this something? So I was going through a few of the videos of quantum computing.
Yeah.
So is it something the same? What I feel is these calculations are applicable on the quantum computing as well, I guess.
Definitely. Quantum computing actually uses a lot of linear algebra. So it's about because you don't work with bits there, you work with qubits, which can be 0 0 0 1 1 0 1 1 at the same time. It is simply a 2-dimensional vector.
Yeah. So I was just getting that sense when you are explaining that. I could able to correlate the video with what I've
watched. So that you can take, for example, that would be another application. Okay. But about quantum computing in higher dimensions, I'm not sure where it goes. I don't really work in that field. Okay.
Yeah.
But what I mean to say is that if I expand this to a higher dimensional subcube, which I can draw on the paper, I'll always notice that on the even levels, I'll have ones, and on the odd levels, I'll have zeros, or vice versa. Even if I draw a bigger one, for example, there are exactly 1 1 here. And I see this pattern, right? So this is one application of doing, and this is very useful actually. And this is one application. Another application that I don't really work in is it's used in data science and stuff. You've heard of PCA, LDA, and so on, I think, right? Have you heard of that?
The PCA, of course, we have done that, but not LDA.
LDA is also some, I forgot, low dimensional approximation. Works in a similar fashion. But what is the idea? Well, the idea is that you have lots of data, right? You have lots of data, and because you have so many types of data, for example,
principal component analysis.
Principal component analysis. And they are in a higher dimension, and you have problems analyzing it.
Exactly. Yeah.
So you fitting curves through it, and so what you'll do is you'll just sort of project it onto a smaller dimension, and then analyze it. Project it onto another dimension, and you'll analyze it separately, and then combine the results to get a better curve fitting. Yeah. This is principal component analysis. Exactly. So this
this principal component analysis also. Of course, maybe this is the application where it exactly fits, but it also applies. Say, let us suppose we have a huge data, column-wise data, and then we just by our naked eye, we feel that this column is not required for us. So what we do, we just remove that manually that column of data, and we feed the algorithm. Or else, what we do, we train the algorithm in such a way that remove the unnecessary columnized data, which doesn't require to our required output. So in that case, this PCE algorithm will do that in that such scenario.
Yeah, exactly. So
we can also assume. See, let us suppose we have a data with a file of 20 column data. So we can visualize that as a 20-dimensional object.
Yeah, exactly. But it's difficult to work with a 20-dimensional object.
Yeah, of course. Visualize cannot happen, but we can get the results.
Exactly. You can get the result by using projections. That's right.
Exactly. Yeah.
So that is another example of working with applications of higher dimensions, even though we cannot visualize it. Yeah. Satyendra, so you have any other questions? Shall we move on?
Okay, so thank you, sir.
Okay. Great. So, so this and remove it. Okay, put it here. Okay, great. So now let's come back to this. What did we say? A set of vectors are linearly independent if and only if. Okay, if and only if this particular equation, that is on to if on asking what are the scalar quantities that on linearly combining on this set is equal to 0 is equivalent to asking whether setting x1, x2, x3, x4 equals 0 is the only solution that is possible. Okay, so this is a very important concept. Okay, this is a very important concept because the next idea is what is called basis. The next idea is what is called basis. Okay.
Excuse me, sir. I have one more little bit doubt. If it is linearly dependent, means it can be expressed as a span of the vectors. Linearly dependent, then span concept will be there.
Yeah, it will be there. I agree. But I talked about span in the beginning of the class.
Little bit I missed in that part. But it's still if it is linearly dependent means it will be vector span.
Exactly. So no, so if I have v1, v2, v3, and let's say they are linearly dependent, then if they are linearly dependent, then it means that v1 is in the span of v2 comma v3, and equivalently v2 is in the span of v3 comma v1, and equivalently v3 is in the span of v1 comma v2. Why? Because span represents nothing but all possible linear combinations. No, and on saying that v1, v2, v3 are linearly dependent, it means that there is a linear combination of v1, v2 which results in v3, and from that I can get a linear combination that results in v2 also.
So it means linearly independent span is not possible.
Okay. So what you mean is okay, good question. So you mean take a span of a set of vectors, and is it linearly independent? That cannot happen, because span is the set of all linear combinations of vectors in V. But let's take the most simplest case. Let's just take span of a single vector V. Okay, let's say this is my set. But span of this will contain V also. It will contain 2V, 3V, 2.5V, and so on. So already any two vectors I pick from here, it will always be linearly dependent. So if I'm adding vectors to this set, if I add more vectors to this set, these vectors are already within the span. So yeah, if you take take the span itself as a set, okay, if you take the span itself as a set, the span will not will not be linearly independent. Is that clear?
Okay, means it will be not linearly independent. That's one.
Yeah, that's right. That's right.
So can we just put into layman terms, see, within the set of vectors, okay, if we don't have any such relation between them, that can be linearly independent. So if we have any such relation between those set of vectors, then that can be linearly dependent, and then it can form a span.
Exactly. And that relation that you're talking about is linear combination.
Yeah, exactly.
Yeah.
It might be any relation, but we say it as it might be multiplicative, it might be additional, it might be any way.
Exactly. Okay, great. So let's come to basis. Okay. Okay. So we only got to do 2 questions, but it's okay. Let's talk about basis. Okay. Now, what is basis? Basis has the following definition. Okay. Basis. Okay. B. B is called a basis of vector space V if the following conditions are satisfied. Firstly, okay, the elements of B, okay, span V, which means span of, okay, I don't need to write this. So the span of B equals V. Okay, and secondly, B is linearly independent. The vectors inside B is linearly. This is the definition of basis. I'll give you an example. Take the vector space R cube. This is a vector space over reals. I hope you agree. Because if I take any 2 vectors in R cube, it will be in R cube. I mean, their sum will be in R cube. If I take a scalar, a real scalar, multiply it with a vector in R cube, I'll get another vector in R cube. So it's closed. And let's look at the additive identity. The 0 vector will be contained in R cube. Right? So this is a vector space. Now, what is the basis? What is the basis of R cube? Okay. So firstly, span of the basis should be equal to R cube. So on doing the linear combinations of everything in B, I should be able to generate any element in R cube. For example, let's take 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay. This is able to generate any element in R cube by simple addition or multiplication. Okay. And the linear combination basically. What about this? Let's say 0, 0. Oh, sorry. This should have the. No, it's fine. So this is okay. So what about 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0? This is also fine. I mean, as far as covering R cube goes, it'll cover the span. Its span is the same, right? And what about 0, 0, 2, 0, 2, 0, 2, 0, 0. This is also fine. It will span it because I can always do 1 by 2 times any vector here and I'll get 0, 0, 1, and then using that I can generate anything in R cube, right? So all of these will span R cube. But the second condition is that B vectors in B needs to be linearly independent. So this is where the question comes. B is linearly independent. Okay. Now, if you look at this guy, it is linearly independent. Clearly, you cannot form one vector by using the other two vectors. No matter how many times you add this, multiply, whatever, you will never get a one component here because there is a 0. So let me call them B1, B2, B3. Okay. So this is B1, this is B2, this is B3. Okay. So clearly B1 is linearly independent. Now what about B2? Is B2 linearly independent?
It is linearly independent.
If we see 0, 0, 0, so there it can be expressed like B2, it is contains 0, 0. So one of the vector can be expressed as the sum of the other two then.
Exactly.
B2.
You can just do, yeah, exactly. You can just do 0, 0, 0 is equal to 0 times 0, 0, 1 plus 0 times 0, 1, 0. So it can be expressed. So this B2 is not linearly independent. What about B3? Well, B3 is 0, 0, 2, 0, 0, 0, 0, 2, 0, 2, 0, 2, 0, 0. What about this? Is it linearly independent?
So I didn't get that B2 how it is reduced to linear.
So if we need to say that B2 is linearly independent, we need to say that none of the vectors can be created from the other by linear combination. But it so happens that the vector 0, 0, 0 can be created by combining these two. I'll just do 0 times the first vector 0, 0, 1 plus 0 times. Actually, this is not even required. Actually, the second one is not even required. 0 times 0, 0.
Scalar multiplication is also allowed.
Even scalar multiplication is a type of linear combination. Okay. So, yeah, scalar multiplication is allowed. It's not that I need to only add, but yeah. So this is an example of a non-linearly independent set. Okay, so clearly B2 is not basis because one of the conditions is not satisfied. B1 is a basis because both conditions are satisfied. It spans R3 also and it is linearly independent. Finally, what about B3? What about B3? Is B3 linearly independent? Yeah, Satya.
B3 also I think no, because 2 times of 0, 0, 1 it can be written. Okay, 0, 0, 1 doesn't belong to that.
0, 0 does not belong to that.
So 0, 0, 1. So 0, 0, 1 also is not there, I think.
Yeah.
So it is basis. It is basis, I think.
It is a basis. So B3 is linearly independent. Why is it linearly independent? Because if I take any vector 0, 0, 2, I want to create this vector using these two vectors. I will never be able to achieve it because of the fact that I have a 2 here and I have zeros here. No matter whatever I multiply to this vector, I'll get a 0 only in the third component as a third component, and here also as a third component I'll get 0 only as whenever I multiply with any scalar, and when I add them also I'm going to get 0 plus 0 is 0 only, but I need a 2 here. So it's not possible, and therefore B3 is linearly independent. Of course, another way to do it would be using Gauss-Jordan elimination, which would show that it is a full rank matrix. Okay, so full rank meaning rank is equal to n, which is 3 in this case, and B3 is linear independent, so therefore it is a basis. Okay, so now, okay, in layman's terms, okay, what does it mean to be a basis? Basis can be thought of as the smallest set, okay, smallest set that represents the entire vector space. So in a sense, basis is like a blueprint. Using this blueprint, you can generate any vector in the vector space. And what is the method of generating? Linear combination, scalar multiplication along with addition. Okay, if you do it with the basis vectors, you can get everything in the vector space, anything in the vector space. So that is the idea of basis. You get it, right? So now I'll just say a few comments and then close it off. So where was I? Oh yeah. Now what is interesting is that if you have any r to the n, okay, a trivial basis is 1 0 0 0 0 1 0 0 0 0 1 0 and so on till 0 0 0 1. This is always a trivial basis. N items. And what does it correspond to? This corresponds to the axis, right? In a three-dimensional sense, it corresponds to the x-axis, y-axis, z-axis. Because this is the idea that given the coordinates of x, y, and z, I can always represent the point in R cube. Why? Because x, y, and z axis form a basis. If I change my axis to some other vectors, I may not be able to represent every point in R cube because they may not form a basis. But if I have, so similarly, this is the trivial basis and therefore it's also called the standard basis. But my basis need not be standard. So a non-standard basis is what? Is like we saw 0 0 2, okay, 2 0 0, 0 2 0, 0 0 2. Using a linear combination, you can always get a vector in R cube for R cube. Using its linear combination, you can always get any vector in R cube. But this is not the standard axis, right? Yeah.
Excuse me. Like I think this is also standard one because still it is along the x-axis, y-axis, and z-axis. Because we are taking 2 units instead of one.
Yeah. But okay, I mean, you there are different definitions according to different textbooks.
Okay. Like
but what this is not what is called normalized. The length of these vectors is not 1. That's why I'm not considering it to be standard.
Okay. Like what I'm thinking, if like bases are 2 2 0 and 1 2 1 1 2 something like that, like all 3 coordinates are different, not 0 0.
Sure. So maybe you can take this as still a standard basis. That's okay because what you mean to say is they are still lying around x, y, z axis. Of course, you can now think of other. Now you may think of okay. So if I don't want them to lie on x, y, z axis, how do I achieve that? How do I achieve that? If I don't want them to lie on x, y, z axis
by rotation. If I'm going to rotate that, so now the basis will be something different.
You could do that, but what will be the angles of rotation? If you get it right. So this rotation I rotate to this side, let's say, and this rotation I do it to this angle, and this axis I rotate to Yeah, I think it'll work. That'll work. Sure.
Rotation. Maybe I think angle of degree of angle would be 90 degrees because.
Yeah. I mean, no. If you
each angle, each axis would be perpendicular to each other.
Yeah. That is true. But each of the axes you want to be perpendicular to each other. So you want something like this, where they are perpendicular to each other. Okay, you want something like that. And if you recall, can you think of a concept with it where all the vectors are perpendicular to each other?
Something like orthogonal. I don't remember the exact name.
Yeah.
I missed it. Orthogonal projection.
Not projection. Orthogonal vectors. Okay. But more specifically, the cross product. If you remember, given two vectors, you can get a vector perpendicular to both of them. If the two vectors were already perpendicular, then the third vector will be perpendicular to both of them, so it will form an axis, you can say, or a basis in that sense. Okay. Now, but for that, the starting vectors need to be perpendicular to each other. But the question is like, if I have two vectors, let's say, and they span some vector space. Let's say if I have two vectors and they span, and I look at the span, they have vector space. You want to ask if there are these nice vectors which are like the standard basis only. Okay, which are like the standard basis, and they are perpendicular to each other. And like the standard basis, they are normalized in a sense that their length is 1. Okay, so how do you get that? That I hope you remember from the previous lecture. There was something called Graham-Schmidt decomposition, Graham-Schmidt process. So it gives you orthonormal vectors. Vectors which are orthogonal to each other and they are normalized, means their length is unit. Okay, so these are how all these concepts. Sorry, my watch fell off. So these are how all these concepts are interrelated with each other. Okay, and so yeah,
it's A and A transpose will be I think so. Orthonormal vector it will come.
Exactly. If you have a set of orthonormal vectors, then that set, if you represent it as a matrix, then it will form what is called an orthogonal matrix. That's right, where A inverse is equal to A transpose. Right? Good.
Yes, sir.
Yeah. So now, okay, we don't have time now. Okay, but it was asking that, okay, fine, if they are not linearly independent, then find the non-trivial linear combination. We found that by setting t equals 1. Now it is saying find a basis for the span of these vectors and hence determine its dimension. So that's what I would like you guys to try, okay, offline. So now try to find a basis for this. But how do you find a basis for this? Well, what we've done essentially is, for this particular set, we've shown that they are linearly dependent. V4 equals V1, V2, V3. So you can drop one of these vectors and check whether the remaining vectors are linearly independent or not. If they are linearly independent, then good, they form a basis. If they are not linearly independent, then what you'll do, you'll check the dependence. If there is a dependence, you'll drop one of the vectors and then find the set of linearly independent and keep reducing the dimension until you get the basis. Okay, we don't have enough time. Maybe I can demonstrate it next week. We could only do 2 questions, but it's all right. Okay.
To construct the basis, what has been explained in the lecture, that concept we are going to use. Like one of the vector will fix, and the second vector we are going to project like V. Suppose second vector is V vector. So V minus projection of V on U, and suppose the third vector is W. So in that we have to subtract what W
No, that is
minus.
that is if you want to find orthonormal basis.
Okay.
Okay.
So
If you yeah.
Because that question was to construct the basis. I
Yeah,
think
but a very specific kind of basis. This one, yeah, this is just basis. This
so how to construct the basis that I was thinking of with this like V1, V2, V3, we have to construct the basis. I think that is the question last part. D part. So what will be the approach that I was thinking to construct the basis?
Yeah. You can do that process. That is called Graham-Schmidt.
Okay.
That is called Graham-Schmidt. You can use that, but that is if you want a very specific kind. Okay. But here you need not use that process. I mean, it's like using a hammer to kill an ant. Okay. So you need not use that process. It's okay. But there is a simpler way that you can do it. That's all I'm saying.
So what will I going to write, sir? Can you write that part?
I want to just can you give me 2 minutes? My laptop is out of charge. Okay, I'll get my charger. Okay, else this I'll lose the recording. Just give me one.